Okay, so hello everyone, I'm Moha and I'll be starting with Boolean algebra and logic gates. So as Karthikeya said, many of you might be knowing this. If you have any doubts, you can stop me in the middle and ask, or you can type it in the chat also. Okay, so let's start. So I'll give you a little introduction of what does a digital system actually mean. We are all surrounded by so many digital systems, like whatever laptop or phone you are using right now, and memory devices, audio devices. So what does a digital system actually mean? So a digital system actually mean that any system which basically generates, processes, and also gathers any information digitally. By information, I mean anything, data, audio, video. It gathers and processes all the information digitally. Now, what does digitally mean? So digitally, it means in a combination of zeros and ones. So basically, it follows binary number system. So hence, for designing of these digital systems, we require components that can store and process such information. So here's a microprocessor, a basic unit for processing information, and this is a RAM. So now any system, to denote any system digitally, we need a set of rules and also some symbols so that we can denote such systems universally. There should be no debate as to how a system or a logic expression should be like represented. So Boolean algebra is a way to denote these systems mathematically and with global acceptance. So here's Boolean algebra, which is a foundation for digital systems. So what is Boolean algebra? So Boolean algebra is a branch of algebra where a function, you can say a logic expression or a function for a system, is represented by combinations of variables. Okay, so now what is a variable? So conventionally, any letter of English alphabet in capital can be used to denote a variable. So what is a variable? So let's say assume a variable, say x. So a variable in Boolean algebra can take two values, true or false, 1 or 0, high or low. So you can any variable can take two values. You can say anything like true, false, high, low. But generally mathematically we use the values 1 and 0 to denote a variable. Electronically speaking, 1 and 0 means current is flowing and current is not flowing. So a switch is closed or a switch is open. So because of it, Boolean algebra is also known as switching algebra, because the switch also denotes two states, open and close. Okay, so these are the laws of Boolean algebra by which logic expressions are simplified, and any logic expression follows these laws and any variable follows these laws. So for any variable x, here x can take two values, 1 or 0, x dash, x bar or x complement, it represents inverse of x. You can pronounce it as x inverse or x complement. Now this denotes inverse of x, as I said. So if the value of x is 0, x complement will represent 1. If value of x is 1, then x complement will represent 0. So basically it's inversion, it's known as inversion. For any variable x that can take two values, zeros and 1, the following holds. So now the laws of Boolean algebra are starting. Like these are a bit theoretical, but they are important. So x plus 1 is always 1. Here remember that x can be anything. Irrespective of the value of x, which can be 0 and 1, these laws hold. So x plus 1 will always be 1, x plus 0 will always be x, x into 1 will always be x, x into 0 will be 0. So these are four basic laws. Next comes the idempotent laws. X plus x will be x, x into x will be x. X plus x dash will be 1. This is the complement law, two complement laws. Like you can verify it yourself, like that if x is 0, x complement will be 1. So the sum will always be 1. X into x complement, that is x multiplied with its own inverse, will be 0, because naturally every time one of them would be always 0. Next is involution, which we already discussed in the first point. X, like we didn't discuss it exactly, but it's quite obvious that x dash of dash, x bar of bar will be x again. That is involution. So again, there are some more laws. The commutative and associative laws, as you can see here, are quite obvious because even our normal algebra follows them. So does the Boolean algebra. The absorption laws are quite important. You can see the first law, x plus xy is equal to x. Take x common from here, you'll get 1 plus y. As said in the previous slide, 1 plus y would be 1. So finally, you'll get x. X into x plus y, simplify them, multiply, open the bracket and simplify them, x into x plus xy, it would be again x. So the absorption laws. Next are distributive laws. The first one is obvious, even normal algebra follows it, x into bracket y plus z would be xy plus xz. The second law is important because normal algebra does not follow it, but Boolean algebra follows it. X plus yz is same as x plus y into x plus z. You can assume any values of x, y, z, 0 or 1. This law will hold. Unlike normal algebra where x, y, z can take any value on the real number line. So this is an important law. Remember it. It would be helpful for simplifying expressions. Next are the De Morgan's laws. You all must have heard these. X plus y dash is equal to x dash into y dash. Xy dash is equal to x dash plus y dash. Take any values of x and y and simplement, and you can verify these laws, the De Morgan's laws. Now here are some other useful laws which follow the principle of distributive laws, like x plus x dash y is equal to x plus y. If you use the second distributive law, you can verify this expression. Next is x into x dash plus y is equal to xy. Obviously, x multiplied with its inverse would be 0, and x into y. So finally, you'll get xy. So here's an example which will you guys understood this much so far, right? No doubt. Hello.
Yes, we understood.
Okay. So here's a logic expression. You can say, let's consider a system with this logic expression. And you have to design this system with when the session will be over, you'll be able to design it using gates, muxes and other things. So you are told to design this system. So it will require a certain number of gates, muxes and all. Now, using the laws of Boolean algebra as discussed previously, we'll simplify this expression. So in the first step, the De Morgan's laws are used to simplify this part and this part. You can follow, and then b dash would be 0 over here, brackets are open and written b dash would be 0. Finally, these will be remaining. Take ab dash common, 1 plus c would be 1. So finally, this would be there. So if you are told to implement this thing and this thing would be obviously easier. It will require less component, and also it is called an optimized solution. Like minimum number of gates and muxes will be used to implement this thing. So this is the importance of Boolean algebra. Now over here you can say take a common b dash plus c dash using De Morgan's law would be bc dash. Now if you have done logic gates previously, like in JEE preparation or somewhere, you must know the what is this gate? What does this bc dash represent? Like which gate? Can anyone tell? Format xy dash. NAND gate, yeah. It's NAND gate, yeah. BC dash. So obviously I'll take logic gates later. So if anyone doesn't know, it's fine. But yeah, it represents a NAND gate. So this is a much easier form to implement than this one. Okay, so next is logic gates. So logic gates can be said as fundamental units for processing information. So why are they named so? What is the reason behind the name logic gates? So they take a certain number of inputs, as you can see in the symbols here, and they'll give one output based on certain logic. Like there'll be a logic behind them, and based on that they'll give a certain output. So I have put all the major gates over here and tabulated them. These are the symbol, universal symbol. You go to any website or any software, these are the symbols for these particular gates. And these are the logic expression for which we use these gates for. And this is the remark, so you can easily remember what a particular gate does. So let's start. First up is NOT gate. This is the symbol for NOT gate. Its logic expression is A complement. What does a logic expression mean? That when I give A as the input, I get A complement as output. So what is the remark? Flips the value, as we already discussed, inversion. Next is AND gate. Logic expression AB. This is the symbol. I give A and B as inputs and I'll get AB as output. Remark is all high, then high. What it means is that when both the inputs are high, that is both the inputs are 1, 1, only then the output would be 1. Otherwise the output would be 0. Next is OR gate. This is the symbol. This is the logic expression A plus B. Remark is all low, then low. So when both the inputs are low, only then the output would be low. Even if one of the input is high, output would be high or 1. Or obviously if both the inputs are 1, output would be 1. Next is NAND gate. As you can think from the name, not AND. It means it will give totally inverse values of what an AND gate would give. So it's a NOT gate placed in front of an AND gate. Or so it's the remark is all high then low. What was the remark for AND? All high then high. So here it's totally reverse, all high then low. This is the logic expression A dash plus B dash or AB dash. This we discussed in the previous example. So this is the symbol for NOT gate. So you can see whenever this open circle is placed in front of a gate, it represents an inverter placed in front of a gate. Sometimes you may also encounter such open circles at input side. So there you can say that this inverter is placed over there. Right now, so it's a NAND gate. Next up is NOR. Remark is not OR, all low then high. In OR it was all low then low, here it's all low then high. Logic expression A plus B complement or A complement B complement. Next is XOR. This is obviously one thing I forgot to tell. NAND and NOR gates are universal gates. You can get any logic expression or even any other gate using the combination of these two gates. Yeah, so remember this, these are the universal gates, two universal gates. Okay, so next is an OR gate. This is the symbol for OR gate. Logic expression A dash B, AB dash. So remark is if different then high. So if A and B, both the inputs are different, only then the output produced would be high, like 1, 0 or 0, 1. If the inputs are same, 1, 1 or 0, 1, output would be low. Next is XNOR gate. This is the symbol and this is the logic expression AB plus A dash B dash. Remark is not XOR. That is if same then high. So if both the inputs are same, like 0, 0 or 1, 1, then only output would be high. Otherwise it would be low. Okay, so now let's simulate these gates on circuit bus. Okay, so this is the simulator for circuit bus. If you guys have opened it, you would be seeing a blank screen here. And here are the circuit elements. You can pick input from here. This is the input block. This is the output block. You can also take an LED. Here I have just stuck to the zeros and ones, the output, because it's related to Boolean algebra. Also from here you can get the gates. If you have any doubt in simulation, you can stop me and ask. Okay, so I've already made the circuit for speeding up. Okay, so first up is NOT gate. We saw the symbol. This is the symbol for NOT gate. Yeah, NOT is a unary operator, so it will only take one input. So it is connected with this. Okay, there are two inputs here, but NOT will only take one. You can see here the input is 0, so output is 1. If I switch the input to 1, output would be 0. Okay, so next is AND gate. AND gate. Now, when you select the gate, you can see here the input size is mentioned. So you can take as many inputs as you want, but here I have just taken 2 for simplicity. So okay, AND gate, we already saw it requires both the inputs high to produce high output. Here both the inputs are low, so output is low. If I switch one of them high, still the output would be low. If I switch both of them high, only then the output would be high. Okay, so next is NAND gate. If you would have seen when I was explaining AND, NAND was giving totally reverse outputs to AND. Let's switch both of them back to 0. Okay, both are 0. Output of NAND is 1. It will be 0 only when both the inputs are 1. I switch one of them high, still the output is high. If I switch both high, only then the output would be 0. Next is an OR gate. It will be low only when both are low. Right now both are high, so output is high. You can see even if one of them is high, the output is high. I switch both of them to 0 and output goes to 0. Next is NOR gate, like you can verify it yourself. Hello.
Vasant, do you have a doubt?
Sorry, that was a mistake.
Okay, cool. Cool, Moha, continue.
Okay, yeah, so NOR gate, you can verify it. It will give exactly reverse output of what an OR was giving. Next is an XOR gate. So what was the remark for XOR? That if different, then high. So right now both the inputs are same, 0, 0. So output is low. I switch one of them high. So the outputs are different. Output goes high. Okay, as the order doesn't matter in any of the gates. So again 1, 0, output is high. I switch both of them high, output goes to 0 because the inputs are same. Next is XNOR. The output would be totally reverse of whatever the output was for XOR. The inputs are high, then okay, the inputs are same, then the output would be high. Here the inputs are same. Okay, so the inputs are different here, so the output is 0. Okay, so that's it from my side. Next, Kartikeya will continue. Do you have any doubts? If you have any doubts, you can ask right now, or even at the end of the session. But if you have, then you can ask me.
Okay, so before I start, I just want to know how many of you guys don't know binary. Please raise your hand or chat or any way it's fine. How many of you guys don't know binary? It's fine if you don't know. I'll like explain whatever is required for this session. Okay. Okay, so we'll know a small bit of this. Binary number is a binary number system is another number system like a decimal number system. So in decimal number system, basically we'll have numbers from 0 to 9, right? 0, 1, 2, 3, 4, and so on until 9. And then after 9, the next number would be 1 to the left side of the least significant bit, and then it will go back to 0. Same way, binary number, it would be 0, 1, and then after that nothing will be there. After the 1, it will go back to 0, and the next significant bit, that is the bit to the left of it, the digit to the left of it, will be 1. That is all you need to know for today's session. So I'll be sharing the slides with you guys. Are the slides visible?
Yes.
Yeah.
Yes. Yes.
Yes.
Yeah, so what we'll be learning here is there will be a truth table. What a truth table is that so if you have say two inputs A, B, they can take two values 0 and 1, right? So when you for that combination, what output you'll get, you can see it in truth table. That is a truth table, and Boolean expression is like what you saw x plus y and stuff like that in the last slide. So what we'll be doing is converting the truth table into Boolean expressions in the form of SOP. SOP means sum of products expression. To do this, first we identify all the combinations where the output is high, Then we write a product form of the combinations. At last, we sum them together. I'll show you guys with an example. So first, let's take a truth table. So here, A, B, and C are the inputs. So if you say the circuit is something you don't know, but you know that if you input 0 for A, 0 for B, and 0 for C, you get output is 0. Similar way, all these things. For these combinations of input, you get these outputs. Now, what we do is identify the combination where the output is high. High and low basically means 1 and 0, high for 1 and low for 0. So we'll see, we have it here, here, and here. So here we have the first thing. Let's do this first. So the product form of this combination would be this A bar B C. This can be also called A dash. So why it is A dash B C is that we need to make a sum in such a way that we need to make a product in such a way that the output should result in 1. That is what we need. If you substitute all of them, A as 0, A dash will be 1, B is 1, and C is 1. So A dash B C is again 1. But if you put any other combination, you'll see that it will result in 0. Only for this specific combination, it will be 1. But we also have two more combinations like that where it is 1, these two which have been marked. So for those also, we need to find the product expression. See, for this it's A, B, C dash because C dash is 0. And for this is ABC because everything is 1. Has someone not understood anything until what I've said? Any doubts? Am I going fast or anything?
No, it's fine.
Cool, cool. So the sum of the product form would be A dash BC, ABC dash, this is plus ABC. Why we are doing sum here is it can be A dash BC or ABC dash or ABC. So what we're doing them is ORing them together. Or also means plus here and also means the product here. So that is why we're doing that. It can also be written as sigma of 367. Generally, you would have learned in math that sigma is for summation and pi is for multiplication. So sigma means basically addition. Here, why we wrote 367 is that if you take the binary equivalent of this, so as people told they don't know binary, I'll just explain it a bit more easily. So for 0 and decimal, it will be 0, the binary equivalent. For 1, it will be 1. For 2, as binary won't go out after 1, this will become 0 and this will become 1. For 3, again, you'll increase 1 here. So it will be 1, 1. And for 4, see here you add one more 1 here. So 1 plus 1 will be 1 carry out to the left side and 0 here. And there again 1 plus 1 will be 1 carry out. So it will be 1, 0, 0 and so on. So you get this is the binary equivalent of 6. This is the binary equivalent of 7. And this is the binary equivalent of 3. So you basically write it as sigma of 3, 6, 7. Now, this is how you convert truth tables into Boolean expressions. Next, I'll give you guys how to do Boolean expressions to logic gates. Let's take an example of XOR gate. You've seen the XOR gate, right? So this is the truth table of the XOR gate. If either of the input is 1 and the other is 0. That's basically if both inputs are different, it's 1. XOR basically means exclusive OR. So it should be exclusively one of the input should be high and one of the input should be low for two input gates. And if both inputs are same, the output is 0. So can someone tell me the product form of this thing? Like we discussed the product form there, right? In the previous slide.
A bar
A
B.
B dash.
Yeah, cool. It's A
A
dash
dash
B.
B.
And for the next one,
A B dash.
A B
cool.
dash.
A B dash. So basically, the thing for XOR gate, the Boolean expression in sum of products form would be A dash B plus A B dash. And now I'll show you the implementation in this site called Circuitverse, which for which the link has already been shared for you guys in the chat. So XOR gate, right? You could obviously. Is Circuitverse working for you guys? Anyone? Organizers also, please check and let me know. Okay, fine. It's not working for me. So I'll open a similar thing, similar application called Logisim. It's the similar thing as Circuitverse, but it's a different user interface it has. So let me share the screen for that. So we choose an input. We choose two inputs. This is A. Can people see this? I think it's too small, right? That's why I wanted to do it in Circuitverse. But for some reason, it's not working for me. Maybe maintenance problems. Yeah, so I'm audible, right?
Yeah, you are.
Yeah. Yeah, yes, you are.
Cool, cool. So the expression we saw was A dash B plus A B bar. A dash is just A with a NOT gate. That makes it A dash. So we take a NOT gate and we connect a wire to it. And
Karthike,
B,
you
yep,
can zoom also on left corner, left
yeah,
down corner. See, you can zoom. Left down corner, there's some 100%.
cool, cool, cool. Thank you, thank you. Yep. So now you guys can see it properly, right? So A bar B. The thing which comes out of this is A bar. If you see the thing properly, A is 0 here, so there's a dark green line, and here there's a light green line, which means the circuit is high, or which means the output is 1. Now we are supposed to multiply it together, or we can say AND them together. So we connect these two to an AND gate. So this is the output, and then we have AB bar, right? So we just take the thing out of AB bar. Here you can see that there's a, what do you call, circle type of thing. If that thing is there, it means it's connected to that wire. Here it's not there, it means it's not connected. The both wires are not connected. So we take A, and from here we take B bar. So we take B initially, and then we take a NOT gate. Now this will become B bar. Now similar to that, we AND them together. and now we need to OR them together. Sum of products, right? We did the products here, and now we are doing the sum. Sum is equivalent to OR gate. This thing product is equivalent to AND gate. So we're getting the output. You could choose an output here. So 0, 0 is 0. 1 second. Let me take an XOR gate so that it will be, you know, clear whether I'm doing it correct or wrong. So I just took LED so that it won't be that boring. 0, 0, the output is 0. Here also you can see that the LED is not lit up, so it's 0. 0, 0, 1. Here the output is 1 and the LED is also glowing. So we both know that these outputs match, and for our input, we know that we're getting correct outputs. And for 1, 0 also we're getting the same thing, and for 1, 1 we are getting 0 again, which means our XOR gate worked. This is how you simulate stuff here. Now you guys can do it if you want, and if you have any doubts you can ask. I mean, you can't do it in circuitverse, I guess, probably it's not working later. So if you guys have any doubts with this part, you can ask. So I'll assume that you guys don't have any doubts. I'll move to next topic. Until this point, all of you guys might have done a bit in physics, might have done a bit in computer science and stuff. But from here, I believe you might not have done it. I mean, I did not do it in my 11th and 12th also. So first component we're presenting to you is adders. So what adders are? Adders are components used to add two binary numbers. Now, there are two types of adders, half adder and full adder. Half adder adds two binary 1-bit numbers. So 1 bit is just 1 digit. You would have learned it in CS now. 8 bits is a byte and stuff like that. So 1 bit, half adder adds two binary 1-bit numbers, and full adder adds three binary 1-bit numbers. Now half adder, because it adds two binary 1-bit numbers, it has two inputs and it has two outputs named sum and carry out. You'll know what these are very soon. And full adders have three inputs because they're adding three 1-bit binary numbers, and the outputs are again sum and carry out. So you'll know the why we need to do this. So A and B can take inputs of 0 and 1. First case, A and B are 0 and 0. Sum is 0. Second case, A and B are 0 and 1. The sum is 1. Third case, 1 and 0, commutative law, it doesn't really change for addition. So the problem comes here. Because we are doing combinational circuits, that means we're using gates like AND, OR, etc. Basically, we're using a circuit, and the binary number is just we are sending a signal. It can be voltage or current. If it is being sent, it's high. That's basically 1. If it's not being sent, it's low. That's basically 0. So with the circuit, all we can do with two things, we have two inputs, right? A and B, which are both wires basically when you're implementing it. So the combination of those two could result only in one more wire, which would be an output. So this is also a single bit. So when you take the fourth case, 1 plus 1, you need 2 bits. The left bit, the sum is 0. Here the 1 is carried out. So the sum is called 0 here, and the 1 is called carried out. So in the last case, the sum takes up 2 bits, as I said. The next significant bit, that's basically the one to the left of it, is called carryout. Now let's look at the truth table of the half adders. 0, 0, the sum is 0, carryout is 0, 0, 1, the sum is 1, the carryout is 0, 1 plus 0, it will be the same as 0 plus 1, and 1 plus 1, the sum is 0, the carryout is 1. You guys understood this, right? Or do you need me to repeat
Yes,
anything?
yes.
Yes, bro, we understood.
Yeah. So implementation of half adders. So I'm sorry. 1 second. Sorry. Uh, so I'll start the slide again. Yeah, so what I want to ask you guys here is basically if you take two inputs, any output could be listed as the 7 gates which you were shown before. So for the sum, what gate do you think should be correct? What gate should be used so that the sum output will be like this?
XOR gate.
Yeah, XOR gate, correct. And for the carry out?
And
And
Yeah, yes. So that is what I
And
mentioned
gate.
in the next slide. I just wanted it from you guys. So it has logic 1 when A is 0 or B is 1, or A is 1 and B is 0. It's XOR gate. And the next one is AND gate basically. Now, as I said, luckily I don't have circuit was working, but this is how it comes out. You take two XOR gates. I mean, you take two inputs and you take two outputs, XOR them, that will be the sum, and AND them, that will be your carryout. Thank you guys. Now I'll be handing it over to Malya, I mean Rohan.